Hi everyone. Before discussing about proportional and integral and derivative control action, I would strongly recommend you please watch this video because in this video I will cover all the variables associated with the control system and how we need to write the variables with respect to time and how the variables are going to change with respect to time. All these things I will explain in the preliminary video, and once you go through this video, then the foundation for proportional and integral and derivative controller will be given properly. So I sincerely advise first watch this video and then watch the next video. Okay, so let us consider a simple example here where we need to monitor the level of the water inside a tank. So the tank height, it is given like 2 meters here, and already there is some liquid or water inside the tank, and the height of that water inside the tank is 0.5 meter. And I have also mentioned one more trigger point here, that is nothing but 1 meter. Now if you see, these are the tank parameters, and when you see the outside of the tank, we are having two pipes which are connected to two control valves through which the liquid can enter into the tank through the first valve and the liquid can exit from the tank through the second valve. The level of the water is monitored by the level transmitter. This is called transmitter, and in instrumentation we have studied very clearly that a transmitter is a device which converts the physical variable into current. Now the transmitter, level transmitter, converts 0 meter to 2 meter water level into 4 milliampere to 20 milliampere current. It is nothing but it is in the standard range. Now the relation between the current and water level can be given like this, that is current equals to 8 milliampere per meter into h of t plus 4 milliampere. Suppose by chance if the water level is at 0.5 meter, if the water level is at 0.5 meter, then the current will be equals to 8 milliampere. That is 0.5 into 8 milliampere, 4 milliampere plus 4 milliampere. Altogether it will be equals to 8 milliampere. Now those people who understand how we can convert the water level into current by using the standard equation, now if you take the reverse action, then easily we can, current can be converted into water level by using this equation. Clear? So now let us go one step beyond this one. So water level will be continuously monitored by the level transmitter, and this water level will be given to the error detector. And for this error detector, this circle where you are able to see plus and minus symbol, this is actually nothing but error detector, and this error detector subtracts two inputs. One is the current coming from the level transmitter, and the second is current coming from the set point from the control room. Okay, now let us look at what happens here. So who will going to apply the set point? Obviously the engineer will going to apply the set point, because we always expect the water level should be at our desired point. Our desired point or our requirement or reference input is actually called as a set point. Now let us assume that the person or the engineer in control room, he mentioned the set point as 0.5 meter. Then corresponds to this water level. That means the engineer is expecting 0.5 meter water level inside the tank. So when he press like 0.5 meter in control room computer, then correspond to that, back-end closed loop control system will consider the current IS of T. Now what is the relation between current and water level? I already told you the relation, wherever you find or wherever you require the relation between water level and current, we should use this one, and the water level and current we should use this one, irrespective of the device. Now corresponds to 0.5 meter, definitely there will be some current that will be produced here. So how much it will be? So just if you keep 0.5 meter, then you will be able to understand the required set point in this case is equals to 8 milliampere. Clear? So that value will come here and the measurement value will come from here. Both will be subtracted and it will be given as error E of t here. And this error E of t will be taken by the level controller and it will generate current in the standard region 4 milliampere to 20 milliampere. Now it is a duty of the controller, based on the error it is recognizing, it will generate different amount of the current in the range of 4 milliampere to 20 milliampere to turn this valve, because this is electrically actuated valve. If the current applied to this valve is changed, then the position of the valve will going to change. If the position of the valve is changing, then the flow rate will going to change. Now let us discuss the ranges of each and every variable here. So we have seen that the input flow rate can change from 0 meter cube to 100 meter cube per second, and the output flow rate can change from 0 meter cube per to 100 meter cube per second. That means fully open or fully closed to fully open, fully closed to fully open. Now the interesting fact here is the water level can change from 0 meter to 2 meter here, and the current transmitted can be changed from 4 milliampere to 20 milliampere. Now the great thing is even the level controller is allowed to generate the current in the standard range only from 4 milliampere to 20 milliampere. This means that all these ranges are fixed for the devices. Now let us understand the problem much more deeply. Now suppose let us consider a simple time scale here. Assume that 8 am to 9 am, that is 1 hour time, I have segmented like one segment, and 9 am after I am breaking that into another segment. For example, let's consider like this. Initially the tank is almost from 8 am, that is 8 am time, to 9 am, up to 9 am, that means less than 9 am, 8 am to 9 am. The tank is at steady state, or the tank is already having the water inside the tank, like 0.5 meter is the height. Suppose, how can we think this as mathematically? So as I said, 9 am will be considered as a t is equal to 0 seconds now. That means the starting point. And before 9 am, just before 9 am, that is 8:59 am will be considered as a t is equals to 0 minus seconds. That means just before 9 o'clock. And just after 9 o'clock, it will be considered as t is equal to 0 plus. That means after 9 am. So, suppose hereafter if I say t is equals to 0 minus seconds means that is just before 9 am. Now we need to understand this problem into 10 segments. What happened before 9 am and what will going to happen after 9 am and what will going to happen exactly at 9 am. If you are able to understand these three, then automatically the problem will be very simple. Now let us consider like this. Just before 9 am, let's consider that the water level in the tank is equals to 0.5 meter, which is at steady state. That means almost from 8 am to 9 am, I am considering that the water level is at steady state. So here it will be written now as water level, that is nothing but process variable. How can I write this one now? That is going to be Hm of t, right? Now exactly at, I am looking exactly at 8:59 am means t is equal to 0 minus second. Now can anybody tell this one? Hm of t, now it should become like Hm of 0 minus, which is actually equals to how much? Hm of 0 minus, that is 0.5 meter. Clear? So that means exactly at 8:59 if you see, water level in the tank will be equals to 0.5 meter. Now I would like to ask one question. May I know how much water level we require initially? That is 0.5 meter. It was already given. That means 8 am to 9 am, the set point is fixed at 0.5 meter. So that means I can say Hs of t is equals to, right now it is going to be Hs of 0 minus exactly at 8:59, right? So that is equals to 0.5 meter. Clear? This is set point in water level. What about the current signal at that case? So I can say the current signal Is of t can be given as, now Is of t we know that can be from here. So this is going to be like this. Every time 8 milliampere per meter into Hs of t plus 4 milliampere. This is the conversion between Hs of t and Is of t. Anyway, Is of t, as we are at 8:59 am, just before 9 o'clock, the current in this can be, set point can be given as Is of 0 minus, how much it will be Is of 0 minus? Is of 0 minus is equal to 8 milliampere per meter into Hs of 0 minus plus 4 milliampere. Hs of 0 minus is 0.5 meter. 0.5 into 8, that is going to be 4. 4 plus 4, 8 milliampere. So that means initially the current generated by the set point line is equals to 8 milliampere at 8:59 am. What about the current signal here? Now when you come back to current signal, that is Im of t, can be given as simply Im of 0 minus, and that is also because water to current relation is same either this side or this side. Okay, so even here also it will be at 8 milliampere. Clear? So now if you look at error signal in water level, how can I write error signal? This is the difference in these two currents or difference in the heights. Both will be correct only. Now this can be written as error E of t, right? So that should be equal to how much? Hs of E of 0 minus, that will be equal to Hs of 0 minus minus Hm of 0 minus, and these two values are same. Hs and Hm both will be same at 8:59:59 am. Right, so this can be written now as 0 meter. That means at 8:59:59, just before the 9 am, we don't have any error. Right, we don't have any error. So that means just before 9 am is actually written as t is equals to 0 minus seconds. There is no error in water level. What about current signal? That is, even if you look at the current signal here, E of t can be written as E of 0 minus, that will be equal to IS of 0 minus minus Im of 0 minus, that will come down to be equal to 0 milliampere. Clear? Right? Now when we look at the controller output here, how much should be the controller output? This is really very interesting thing. That is, controller current can be given as IC of 0 minus is equal to. Now look at carefully. So here error is 0 milliampere, right? So if you take in current, so error is 0 milliampere. But this should generate some current. Otherwise, suppose if this current is equal to 0 milliampere, then what will happen? Or 4 milliampere, then the wall will be at extreme position, right? But how much we require here? Because we have considered that both are equal, means let's consider that this is 50 meter cube per second, and this should also be 50 meter cube per second here, right? Qin of t is also should be equal to 50 meter cube per second. This can happen at 8:59:59 am if it generates how much current? It should generate 12 milliampere current, correct? That means IC of 0 minus, that means before 9 am, the current generated by the controller should be equal to 12 milliampere even when the error is 0 milliampere, because set point just before 9 am it is 8 milliampere and the measured current is also equals to 8 milliampere here, correct? So if it is not generating 12 milliampere properly, it will not be at 50 meter cube per second. So that means our controller even before 9 am it is generating 12 milliampere current. So that means here we can write down this as 12 milliampere current. So this is the current what we are getting even though when there is no error, right? So this current what we are getting when in the absence of error is called as controller offset or controller bias or controller output with zero error. Clear? All these things will be valid at 8:59:59 am or just t less than 0, which is nothing but t is equal to 0 minus second, just before 9 o'clock. Just before 9 am, the process is already at steady state. Means this value is fixed at 0.5 meter and Qin of t is fixed at 50 meter cube per second and this value is fixed at 50 meter cube per second. This means usually you should write down like this, that is Qin of 0 minus and this could be 0 minus. Clear? So all these values are at steady state just before 9 am. Now let us look at what happens exactly at 9 am. Exactly at 9 am, this person who is present in the control room, he is not interested to see the water level at 0.5 meter. He wants the water level should be at 1 meter. Okay. So that means now this person intentionally applied a change of water level delta Hs of t. Okay, how much he changed? So this extra is going to be 0.5 into u of t. Clear? 0.5 into u of t. That means set point is suddenly raised. Earlier the set point is 0.5 meter. Now the set point is raised to another 0.5 units, and that is fixed for the next 1 or 2 or 3 hours of time. That's why we are indicating like unit step input. Now whatever the variable we are having here, that we should indicate this as a change in set point, and this is the initial steady state set point. Okay, initial set point. Now obviously when we apply this, then how the hs of t will going to change now? Hs of t is equal to initial point, set point, plus some variation in the set point, and this was applied exactly at 9 a.m. I hope you are clear. 9 a.m. we applied this change in the set point. Now carefully if you look at, IS of t will going to change like this. Now how should I write IS of t now? The current can be written now as, definitely initially there is some current, that is IS of 0 minus, right? And now otherwise you can see here how the current will going to change now, because water level is changing here. Hs of t is equal to 0.5 meter, or else I can say delta Hs of t plus initial value is 0.5 meter. Clear? Initial value is 0.5 meter. Now what about Is of t? Is of t can be written here as, when there is some variation in the set point of the water, then naturally there will be variation in the current signal also, right? So delta Is of t plus initial current is 8 milliampere. This is how the current will going to change after t greater than 0, because at t is equal to 0 we have applied this signal, and after 9 a.m. we will be able to see the relations like this. Clear? So let us go ahead. What about Hm of t now? Hm of t, that is water level with respect to time. How it will going to change? Naturally, because of this change in the set point, this value will be changed. When this value will be changed, this signal will change. When this signal changes, then the water level will going to rise. Now this means that we can write down the change in water level plus initial water level is 0.5 meter. Okay? And what about the current signal here? Now the current signal, if you look at, even the current signal also will be like this. The transmitter output will be some change in current plus 0.5 meter. All these are initial steady state values. Okay, because initially just before 9 a.m. the process is at steady state. Now we changed with the set point. Okay, what about water level here? Error in water level will be always Hs of t minus Hm of t, and this can be written as, current signal can be written as Im of t, Is of t minus Im of t. Clear? And when it comes to controller output current, now controller output also will going to change. Correct now, because when you want the water level should be at high value compared to 0.5 meter, then naturally it should generate more current. When it generates more current, then the valve will going to open more and the water level will going to increase because the flow rate will going to increase. This means now the current generated by the controller should also change with respect to set point, that is delta IC of t plus initial current is 12 milliampere. Clear? Right. Now for understanding purpose of the mathematics, which we are going to see in the upcoming videos, let me go for a small notations here. Wherever we have delta Hs of t, that is called deviation, we will write this hereafter as Hs cap of t. This is the deviation, and 0.5 meter is the initial set point, that is Hs of 0 minus. Clear? And Is of t can be written as deviation, some deviation will come in the set point of the current. So here this should be written now as Is of 0 minus. Clear? And when it comes to Hm of t, this delta Hm of t should be written as some cap here, that means deviation plus initial steady state value, that is Hm of 0 minus. And here Im of t can be written as Im cap of t, because deviation we are indicating like cap. Okay, so this is initial value, that is Im of 0 minus. Okay, and error, when it comes to error, Hs of t minus Hm of t we are taking. Correct? So error also can be written here as Yeah, error can be given like this only. No need to change this one. You can keep this, you can keep this one. And when it comes to current here, we should write down this as now IC cap of T plus 12 milliampere. And if you are not interested to see these lines, then you can even write down E of T is equals to E cap of T plus, this can be written here. This is also correct. Even if you write like this also, it could be correct. That is equals to E cap of T plus E of 0 minus. Clear? So E of 0 minus means initial error. Initial error is how much? 0. That is just before 9 am. This is the way how we are going to integrate the variables. Now let me quickly revise what we have discussed here. That is, the water level set point can be given as some deviation in the set point plus initial value. That's 0.5 meter. Now when the set point is deviated from the initial value, when the new set point is triggered, then automatically everything will going to change. Okay. Now let's see what should happen ideally. What should happen ideally? To understand what should happen ideally, we need to represent these variables in block diagram. If I represent all these variables in block diagram, then it will be very easy for you to understand. So next we will going to see how we can represent all these variables in block diagram as well as the graph of each variable, such that it will be very clear to you. Now let us look at the problem much more deeply. As I said, to understand this, you need to know the block diagram and you need to draw the block diagram. So here it is the block diagram where we have controller, actuator, process and transmitter, or whatever the elements we used in the previous example. I have taken the same elements here. Now let us look at with respect to time. It is just before 9 am. Just before 9 am means what? Just before 9 am means T is equals to 0 minus seconds, right? Because we have segmented like before 9 am and exactly at 9 am, after 9 am, right? So what does it mean? Before 9 am, just before 9 am, our set point is actually 0.5 meters. This is what we expected earlier, right? And corresponds to that, it is generating 8 milliampere current. 8 milliampere current. Even we know that exactly at just before 9 am, the water level inside the tank is also 0.5 meter here. And this is 0.5 meter means obviously it is 0.5 meter here. And if it is 0.5 meter, we know that the current to water level to current conversion should bring this to be equals to 8 milliampere, right? So now when we have 8 milliampere here, 8 milliampere here, the error will going to be 0 milliampere. And if the error is 0 milliampere, the current generated by this should be equals to 12 milliampere. This is what exactly we have discussed earlier, right? When it is at 12 milliampere, this should be at 50 meter cube per second, right? 50 meter cube per second, correct? As long as this is at 50 meter cube per second, as a water outlet, water flow outlet is also 50 meter cube per second. Now water level will be exactly at 0.5 meter. This is called initial steady state, and this is how the variables looks like just before 9 am. But exactly at 9 am, right? Exactly at 9 am, that means exactly at 9 am, at 9 am means T is equal to 0 second. We have changed the set point, right? We have increased the set point to be another 0.5 meter. So how can H of T looks like now? That means after T greater than 0. That means we can say now like after 9 am now. After 9 am means T greater than 0. The water level looks like this set point. That is we have changed this some extent Hs of T plus already some water level is there, that is 0.5 meter. Clear? And this Hs cap of T is actually equals to 0.5 times of U of T. Clear? So this is called unit step input applied to the control system, that is 0.5 U of T. Now what about IS of T now? Now you should not write this as like this. Now IS of T, that is current, can be written now as equals to IS cap of T plus initial condition, that is IS of 0 minus. Clear? So this is the amount of current that will come here. Now when you look at the error, so anyway we'll come back to the error. Otherwise you can write down all values of will going to become like this. Error can be equals to E cap of t, right? So this should be cap, sorry, this mention this as a cap here, mention this as a cap. Okay, so if you mention this as a cap, then it will be the meaning of deviation, right? So E cap of t plus this can be written now as E of 0 minus. Now when it comes to IC of t, now controller current will be equals to IC cap of t plus IC 0 minus, that is offset. Now Qin of 0 minus can be given as QA of t can be written as, there should be some deviation in the flow rate also because set point is varied, cap of t plus initial flow rate, that is QA of 0 minus. This is the way how the variables will going to change. But what about water level here? Naturally the water level will be equals to HM cap of t, some deviation plus 0.5 meter is the initial value, that is HM of 0 minus. Clear? So then this is going to be HM of t now hereafter, HM of t, right? And this is IM of t. Clear? IM of t. Now if you look at this, all this block diagram clearly, initial steady states were established very well, right? But what happens is, when the water level is changed or when the set point is changed, then this current will going to change and our water level HM cap of t finally should be equals to HS cap of t. HS of t, if you look at graph, HS of t, it looks like this. T, right? So t equal to 0, and just before 0 water level was very well established, and this is going to be of 0.5 meter here, right? Just before 0. Now exactly at 0 we have applied a change in the set point, and we expect this should be 1 meter, right? And this gap is going to be called as HS cap of t, which is equal to 0.5 times of u of t. This gap, clear? This gap, that means the step height now it is going to be of 0.5 u of t. 0.5 u of t. Now have you looked at this one clearly? From this we can say HS cap of 0 is equal to 0.5 meter. That means the deviation in the required set point is 0.5 meter, and HS of infinite is also 0.5 meter, and HS of any time, that is HS cap of any time, is 0.5 meter. Correct? Because it is a step input. This deviation is 0.5 meter and this is water level 1 meter. So this deviation plus initial value is going to be the total level with respect to time. Right. Now if you look at that water level here, HM of t, we are very much sure that HM of 0 minus is very well at 0.5 meter, but HM of 0 is also going to be 0.5 meter only, because the water level will not change immediately within the limited time, because it forms a capacitive kind of circuit. Water level of HM of t, if you look at this one, HM of t graph, just before, here it should be in seconds, before t equals to 0, the water level in the tank is also at 0.5 meter, right? But ultimately the water level is going to come or should come to 1 meter. So, but unfortunately, ideally what should happen? Even the water level in the tank also should jump, but it won't jump, right? So that means this may be following different patterns. Okay, for example, if I say the water level is smoothly increasing and increasing, getting like this, clear? Right, after some time, this is how the water level is changing, and this change, whatever we are having here, This is actually called as HM cap of T. Clear? This is going to be HM cap of T. That means HM cap of T slowly varies, then automatically HM of T will also going to vary. Ideally, after this much of explanation, you should understand quickly. That is, even after some time, right? It could be better if it happens very fast, but this deviation should be equals to HS cap of infinite. That means after some time, this value and this value both should be equal. Clear? So if both are equal, then I can say the error, let me write down like this, otherwise after some time means it should be infinite, right? Infinite here, right? So error should be equal to 0 meter. Clear? 0 meter, or we can say even 0 milliampere. Clear? So this means that for any control system, ideally the steady state error should be equal to 0. That means this deviation should change slowly and it should be equal to 1 meter. Clear? And if it is a very good control system and this value of water level should be equal to 1 meter as quickly as possible, then I can say this as an ideal control system. So now I hope you understood all these variables very well. Anyway, HM of 0 minus, that means just before 9 am and just after 9 am, both are going to be same. So this can be written as HM of 0 minus or HM of 0. And when it comes to this one, that is Q in of T, even the flow rate will not change. So let us keep like this. And when it be equal to IC of T, where IC cap of T plus IC of 0 minus. So this could be, because even IC of 0 will also not respond properly, but it is better to write IC of 0 minus here. And E cap of T is equal to E cap of E of T is equal to E cap of T plus E of 0 minus. So with this, I have completed all the variables which are actually required here. Right? So in the upcoming videos, we will going to understand how fast we can bring this water level to 1 meter. Okay, by using different controllers, smoothly without any oscillations, and ultimate desired thing is we need to reach this 1 meter as quickly as possible. That means accuracy should be high and the speed of response also should be high. So we will see in the upcoming videos how we can make all those things. To understand the performance of the controller mathematically, one should draw the block diagram of a complicated system or any control system. Suppose, let us say this is the block diagram of this control system what we have been discussing so far. There are two ways to represent the block diagram here. The first one is with respect to time and the second one is with respect to deviations. Right? So I told you whatever happened before 9 am that we considered as a steady state or initial steady state. Whatever is going to happen after 9 am that we considered as deviations. Right? So now as we know that controller will going to have some function. So depending upon the type of controller, the mathematical function will going to change. And the liquid level process is a first order system. That's why we have modeled this liquid level system by a differential equation, that is d by dt hm of t plus hm of t equals to q naught of t. Here ultimately we need to control the water level. That's why the ultimate interested variable is hm of t, and this hm of t, water level with respect to time, that will be controlled by the flow rate, and the flow rate is going to be changed by the controller current, and the controller current with respect to time, that will be changed by the error. Now this error depends on the set point and the current coming from the transmitter, and this current is actually generated by this water level hs of t. Clear? So now as I said, there is a converter here and the conversion is going to follow this relation. That means in the control room, engineer will apply the water level in meters, but backend loop will going to consider that as a current. So suppose here, let us look at what happens here. So as I said earlier itself, each variable can be given as after 9 am plus before 9 am. So E of 0 minus means just before 9 am. E cap of t means after 9 am. Similarly here, similarly here, similarly here. Now let me ask a simple question. What was the initial steady state set point? That we know that this is going to be 0.5 meter, because we know initially water level, the required water level is 0.5 meter, and the amount of deviation what we expected after 9 am is that is extra 0.5 we expected, that is 0.5 into U of t. Now when it comes to current, how should I write current here now? IES cap of t is going to depend on HS cap of t with these relations here. Or else you can simply keep here so that we are going to get IS cap of t. IS cap of t can be given as 4 milliampere U of t plus IS of 0 minus, that is initial current released by this converter, is going to be 8 milliampere. This is before 9 am and this is going to be after 9 am. Now by this time you might understood this diagram clearly. I again say that every variable in this block diagram is represented with respect to time, and cap or deviation is the variable quantity after 9 am and E of 0 minus is just before 9 am. Now the second way to represent the same block diagram is with respect to only deviations. Why? Because these things are already achieved, right? So we need not to use this one again because initially everything was very good, right? So these things are not required. So if you remove all initial steady state values, now the whole diagram will going to change like this. That is, actually we need to track this change in the set point, that is 0.5 into U of t, corresponds to that change in set point, current released by the converter will change, and the whole diagram will try to trace such that this transmitter current ultimately should be equals to 4 milliampere. Then automatically this water level, that is HM cap of t, ideally after some time, at least after some time means large amount of time, we'll call this as infinite, that should be equal to 0.5 meter. Clear? If HM cap of t infinity is equal to 0.5 meter, then automatically HM of infinite can be given as HM cap of infinite plus HM 0 minus, that is before 9 am. So this will going to become 0.5 meter plus 0.5 meter, altogether the water level will going to be equal to 1 meter. Clear? So this means that whatever the controller we are going to use here, that should make this deviation in the water level should be equal to 0.5 meter. Then automatically the net water level will be equals to 1 meter. But if you look at the process variable here, how we have changed here. So as we are using only deviations here, it is your responsibility to write this as a deviation, because it is a linear control system, right? So dHm cap of t by dt plus hm cap of t equals to qi of t. This is how we can take two different block diagrams, but it may be little bit complicated, but I sincerely advise all of you, if you go with this block diagram, that is second block diagram, then it will be very easy to understand the remaining controller's operation. So I sincerely advise go with this block diagram to understand the remaining controllers. Hope you enjoyed the video. Thanks for watching, and if you want to find more of this kind of questions, connect to my channel. Namaste.